In this question, we have a car on top of a 50-meter tall cliff, and that car drives straight off of the cliff with a velocity of 30 meters per second. And we want to know what was the final velocity of the car as it hits the ground. We also want to know how far it traveled from the cliff. This is projectile motion, and that means it has an x component and a y component. The x component is uniform motion, so there is no acceleration. We also know the velocity in the x component, so Vx is equal to 30 meters per second. How do I know this? Well, look at our diagram. The velocity vector is pointed to the right, so it is not at an angle. That means all of the velocity is in the x component, so Vx is equal to the full 30 meters per second. Now let's look at the y component. The y component of projectile motion is free fall, so the acceleration is equal to negative 9.8 meters per second squared. We also know the car's initial position, which is 50 meters, the car's final position, which is 0 meters, and we know the initial velocity in the y component, so VIY would equal to 0 meters per second. I know this because all the velocity is in the x component, so that means there's no velocity in the y component. Now we want to solve for VF, the final velocity as the car hits the ground. VF has an x and y component. That means it's composed of Vx and Vfy. So how can we solve for VF? Well, you can solve for the final velocity of an object in projectile motion using this equation. Vf is equal to plus or minus the square root of Vx squared plus Vfy squared. You might be wondering where that equation came from. Well, let's quickly derive it. All I have to do is draw my velocity vectors. Here we have the final velocity in the y component, Vfy. And then we have the velocity in the x component, Vx. And if we use vector addition, we can add these two vectors together to give us Vf, the final velocity. And what I hope you can see is here we have a right-angled triangle. And I can label each side A, B, or C. And now I can use Pythagorean theorem to solve for these sides. So remember, Pythagorean theorem says c squared is equal to a squared plus b squared. So I will rearrange and isolate for c. Now c represents Vf, a represents Vx, and b represents Vfy. So that is how you derive the equation for the final velocity. But what if you were also asked for the angle of the final velocity vector? Well, looking at our right-angled triangle, we can see we have an opposite side, Vfy, and an adjacent side, Vx. Since we have the opposite and adjacent, we can use tan theta is equal to opposite over adjacent. And then all we have to do is plug in our Vfy and Vx and rearrange for theta, and we get that the angle of the final velocity vector is equal to tan inverse of Vfy divided by Vx. So these are the two equations you'll need to find the final velocity of an object in projectile motion. Looking at this equation, we have Vx, which means we need to find Vfy. Moving to our y component, based on what we have, we should use the Vfy squared is equal to Viy squared plus 2a delta y kinematic equation. All we have to do is plug in our values and solve for Vfy. And what we find is that the final velocity in the y component is negative 31.3 meters per second. Using our Vf equation, we can plug in our values for Vx and Vfy, and when we solve, we find that the final velocity of the car as it hits the ground is negative 43.4 meters per second. And it's negative because the velocity vector is pointed down. Now, what if you were asked to find the angle of the final velocity vector? Well, we know theta is equal to tan inverse of Vfy divided by Vx. We can just plug in those values, and what we find is that the angle of this velocity vector is negative 46.2 degrees. Now, why is the angle negative? Does that make sense? Now remember, Vf came from the vector addition of Vx and Vfy. And notice, the final velocity vector is pointed down and to the right. If I draw our unit circle over here, and I draw our Vf vector, you can see that the angle is below the x-axis, and that is why it is negative. Now let's figure out how far the car traveled from the base of the cliff. Looking at our x component, we know that the x component is uniform motion. So we can use the Vx is equal to delta x divided by delta t equation. All we will have to do is rearrange for delta x. Now we have Vx, but we're missing delta t. So let's use our y component to find delta t. Based on what we have, the easiest equation to use would be our Vfy is equal to Viy plus a delta t kinematic equation. All we have to do is rearrange and isolate for delta t, and what we find is that delta t is equal to about 3.2 seconds. And with that, we can use our uniform motion equation. All we have to do is plug in our velocity and our time, and we find that delta x is equal to about 96 meters. And that's the end of this projectile motion question.